In this lecture, we will discuss the moving average process. A moving average, or MA process of model order Q, is formed by a sum of delayed versions of the input. So I'm assuming that I have a white noise process as input, and then I will delay it. This is a delay operator. Think of it as a shift register. So I will store the value in the register. Then I will, next clock cycle, I will shift it on to this value. Then next clock cycle, I'll shift it on to the next value, and so forth. That means that the most delayed version, E of t minus q here, will have been delayed q steps before it's being added and summed up to produce the output. My filter h of k here is thus the combination of the summed and scaled version of all these earlier inputs. You typically express the moving average process using a characteristic polynomial, c of z, which is then using the z operator. The z operator is nothing but a delay operator, so that means that if I have e of t minus 1 like this is the same thing as zt minus 1 like this. So it's the z minus 1 is the delay. So if I have t minus p like this, it would be z to the minus p y of t like this. So I can extract out the time delays into a polynomial, and therefore I can use this polynomial expression here, z of z, as a characteristic polynomial, which is going to be monic. That means that the first index of this polynomial will be 1. That means that there is a direct path straight through here h time. If I were to compute the mean of the process, that is the same thing as taking the mean of the characteristic polynomial. I will just move the expectation in like this. Notice here that I move using the z operator to write this as z to the minus 1 e of t. The z to the minus 1 is just a delay, so it's nothing stochastic, so I can move it outside of the expectation. Each of these will have mean 0, which of course means that the entire thing will have a mean 0. I can compute the autocovariance function using the standard definition, and what is important with this is that the autocovariance turns to 0 as soon as I pass the lag order greater than q. That means that if I would look at the autocovariance function of an MA process, the lags will turn to 0 as soon as I pass the model order of that process. I can compute the spectrum using the filtering result we had from the filtering lecture, which, if you remember, was the modulo square of the filter times the input spectrum. The input spectrum here is a white noise, so this is just going to be sigma squared identity matrix. The filter gain is written by the characteristic polynomial, so this is going to be c evaluated over the unit circle, so c to the I omega, which is the same thing as saying 1 plus e to the minus I omega plus e to the minus 2 I omega plus and so forth, and of course I should have these factors here, so c1. C2. This means that the spectrum will be found like the absolute of c to the I omega, magnitude square, sigma squared, like this. Very commonly, there is a notational sloppiness, and this is just written c to the omega instead of c to the I omega, and this is also how it's done in the book. This tends to be the normally used notation in the literature, and of course it's not perfectly correct, but it's assumed that you from context will know that this is what's going on. It's just to save people the space of writing the extra letters. Let's look at an example. So here I have an MA1 process. That means that the characteristic polynomial will be 1 plus c1 e to the minus z to the minus 1, as you see here. If I write out the covariance function, you can see that it will turn to 0 as soon as I'm past lag 1. The power spectral density will be evaluating the characteristic polynomial over e to the I omega, so I will replace z with e to the I omega, and what you can see here is that I will get an expression of the spectrum that depends on the characteristic polynomial, such that the roots of the characteristic polynomial will determine where there are nulls in the spectrum. That means if I have roots in my characteristic polynomial here in the unit circle, that will transform into dips or nulls in the spectral density at the same frequency. So this would be frequency omega 0 and this would be angle omega 0. The closer I am to the unit circle, the deeper the dip. Let's look at an example. So this is a realization of an MA1 process. You can see here that the covariance function will turn to 0 as soon as I'm hitting lag 2. That means that I can, just by looking at the autocovariance function, I can tell that this is an MA1 process. Looking at the spectrum, I see that the null sits at the 0, and I can see this also if I look at the characteristic polynomial, which will be then 1 minus 0.8 z to the minus 1, which means that if I solve it, I get that the root in z, notice that the root is in z, is at 0.8, meaning that the root sits here, and I should have a dip in the spectrum at location 0, as you see. Here's an example of an MA2 process, and you can see there's a little bit more structure, so it's more slowly varying. And I also have the fact that the autocovariance function will turn to 0 first at lag 3. Looking at the spectral density, I can see that I have a null at about 0.3. That means that I am expecting the roots of my characteristic polynomial to be about here. And if I extract the characteristic polynomial here, it will be 1 plus 1 plus 1.6 z to the minus 2, which gives me the roots minus a half plus minus I times the square root over 2/5. which is going to be exactly there. For large data set, the mean of the autocorrelation function will be 0, and the variance will be dictated by this seemingly rather complicated expression, and the autocorrelation function will be asymptotically normal distributed, which is an important fact. This means that we can form a 95% confidence interval as 0, which is the mean, and the square root of the standard deviation times 1.96, but as you know, it will be about 2, so we'll just say 2, because there are so many approximations here. For large n, for instance, it's only holding asymptotically, and you will never have asymptotically many data points. For white noise, this simplifies to this very nice expression that I have, that the ACF is bounded by plus minus 2 over square root of n. This means that I can compute the ACF of a process. The first lag will of course be 1 because it's normalized, and then I will have a little bit of a wiggling going on because I have finite data. The question I get here is this a white process or not? If I compute the confidence intervals, this level here should be 2 over square root over n, and as you can see, my estimated autocorrelation functions are inside the confidence interval, meaning that they are not statistically significantly different from 0. That means that anything that's inside this confidence interval we will treat as 0. All these wiggly bits is just the variability due to the estimation performance of this estimator, so they are essentially all 0. We can allow that 1 in 20 is just slightly outside because it's a confidence interval with 95% confidence. So every 1 in 20 can be allowed to be just slightly outside. If the process is an MA process, say order 3, I expect something like this instead, where I now have 3 coefficients that are non-zero outside of the confidence interval. So in this case, I would look at those and say, well, there are clearly 3 statistically significant components that are non-zero, so this seems to be an MA3. There's a function ACF you can use to compute the estimate as well as the confidence interval if you just specify the order of the MA process. So here would be a typical example. Here I have a process that I have estimated the autocorrelation function for, and here you can see I have 1, 2, 3, 4 coefficients that are clearly non-zero. Whereas all of these I will treat as being statistically not significantly different from 0, so they are all 0 in the way I'm viewing it. So therefore, I would treat this as an MA4 process, should be of this form. If I compute the roots of it, I will get these ones, which means that for this angle, since it's further away from the unit circle, I expect the dip of the spectrum to be not as significant, whereas this one is close to the unit circle, therefore the dip should be stronger. And this is exactly what you see in the spectrum. Interesting to note here is also that since you know the spectral density, if you knew the parameters, you can estimate, instead of estimating the spectrum, you can estimate the coefficients of the MA polynomial, and in using those, you can form the spectral density. This is what this curve here is. That is the theoretical spectrum of an MA process, whereas the other wiggly one, this one, is the periodogram estimate. So clearly the periodogram estimate has this problem of variance as we discussed before, and you can see that it has a very strong variability around the spectral density, especially for the higher spectral density, so where the variability will be stronger, whereas the theoretical estimate will be much smoother. This estimate will only depend on the quality of the estimated coefficients, and of course here it is important to say whether those coefficients are well estimated or not. If they are estimated poorly, your theoretical spectrum will be completely off, whereas if they are accurately estimated, your spectral estimate will be very accurate. In short, one can say that any time you have a parametric spectral estimate, if your parametric representation is accurate, this will be much better than if you use a non-parametric estimator that doesn't use a model, whereas if your parametric representation is inaccurate or not well estimated, you can get basically anything. The general advice is therefore that before you know what you have, you first estimate the spectral density using a non-parametric estimator such that the periodogram, examine it, and then you try to build your model to estimate your parametric model and see whether that seems to be accurate before you trust your parametric spectral estimator.